All right, so sorry about the delay here with my stupid idea of turning off the projector. We have now the numerical part of this afternoon. This is Gianluca Frasca-Caccia from University of Kent is going to talk to us about numerical preservation of local conservation laws.
Thank you, Bruno. And so this, as everyone has said already, this talk is connects a little bit with the previous talk of Peter, but anyway, it's also independent. So if someone who's not here before should be able to understand what I'm saying, otherwise I take full responsibility. So yes, it's part of my research together with Peter at the University of Kent, and I'm going to introduce a new strategy for numerical preservation of local conservation laws. So here is an outline of the talk. First of all, some basic facts about conservation laws, focusing mainly on the discrete part, because we have seen already a lot of things about the continuous stuff. And then I'm going to focus on this new strategy to develop finite difference methods that preserve conservation laws. And in particular, we're going to use this strategy, applying it to the DBM equation that you have already seen in an example before, and then to a system of partial differential equation, which is given by the nonlinear Schrödinger equation. And for both of these equations, we're going to see also some numerical tests to see to check the reliability and the robustness of our new schemes. So, of course, something actually, a small framework about what happens in the continuous case also for establishing notation is needed. We are going to consider a partial differential equation, only one at the moment, but then we have seen that these things apply also for systems. This is the notation we are going to use. We have this operator A that depends on two independent variables, x and t. We are considering only a one-dimensional space just for simplicity. All the theory straightforwardly can be applied when you have a higher dimensional space. And then we have the dependence of A with respect to a dependent variable u, and with the square brackets I'm denoting a finite number of partial derivatives of u. So this depends on u and partial derivatives of u and independent variables. And the only assumption that we have on our conservation law, on our PDE, is that it has at least one conservation law. They can have a finite number of conservation laws, can have infinitely many conservation laws, that doesn't matter. The only assumption is that we need one, because that's the point of our talk, we want to preserve conservation laws. So it's the minimal assumption that you can have. Conservation laws is, we have seen, they are total divergences that vanish on the solution of the PDE. And we're just assuming they are non-trivial. Peter has explained already what non-trivial means. And the functions f and g are the flux and the density of the conservation law. And of course, if you have suitable boundary conditions, conservative boundary condition, you can integrate here in space. This term will vanish because of your boundary condition. And the conservation law implies the conservation of also some global invariants. And let's say it is very well known when you have a numerical scheme that preserves a global invariant, that's going to give some more robustness and some actual reliability to your scheme. There are plenty of schemes that are known to preserve global invariant. What we are going to do now is try to preserve something that is even more fundamental. It acts locally, on every subdomain. It applies to all the solution of your partial differential equation. Is independent from the initial condition or the boundary condition. So what we're going to do, it applies for independently of the other information that you have on the solution, so boundary conditions in particular.
But, on this preservation of invariants, you also need, at the continuous level.
Yes, we are talking at the continuous level.
Using the boundary conditions, because if I change the boundary conditions, sometimes I don't have anything preserved.
Yes. So if you have the boundary conditions, you are preserving the global invariant also. If you don't have the boundary conditions, this still holds on every subdomain. This is independent, it's local, so wherever you are looking in your domain, that still holds. And this is what I'm trying to preserve. So I'm saying exactly that. If you have boundary conditions, you will have something else, which is the conservation of the invariant. But if you're preserving that locally, it's more fundamental and implies also the conservation of the invariant when you have the boundary conditions. If not, you're preserving something locally.
And sorry, you're excluding in trivial ones, you said, right? Is that important? Because, in the discrete sense, a trivial one could still be non-trivial, right? Because the divergence of a curl, on the discrete sense, doesn't necessarily need to be zero anymore, for example.
Yes, but there is a parallel anyway between and the discrete case also. Trivial conservation laws in the discrete case are defined exactly in the same way as in the continuous case. So it will be trivial again in the discrete if this is equal to 0 exactly in the discrete setting, in the discretization. So it doesn't give you any information more in any case. So it will not be exactly the curl, but will be maybe.
Okay, so a discrete version would be trivial. That's the, okay.
The discrete version, yes, yes. I mean, yes. We're starting from the yes. And as Peter has explained, if you integrate by parts up to an equivalence, you can factorize any total divergence as the product of the left-hand side in your PDE times a multiplier function Q that is called the characteristic, and this is called the conservation law in characteristic form. This function here depends on the dependent variables has the same dependence as A. And this is a normal product. Here with this index I, I'm just denoting the ith conservation law, so it will change if you represent more than one. So the first conservation law, second conservation law, and so on. And the important result that will be relevant for us is that the conservation laws form the kernel of the Euler operator. That all the divergence form the kernel of the Euler operator. So if you have a multiplier function Q in such a way that this product is in the kernel of the Euler operator, then this result assures you that you can write this product as a divergence, and which is automatically a conservation law, because on solution of A you will get 0. So this is the continuous framework, and it's really everything that we need. And now I'm going to show you how these things develop in parallel also in the discrete case. First of all, if you want to discretize a PDE, the first thing that you need to do is to introduce a lattice and a grid. So we're going to denote with xi the nodes in space, tj the nodes in time, and we're going to consider uniform grids. So delta x and delta t denote the fixed step size. And with uij, there are the approximation of u at the grid points. So these are our discrete notation, which needs to include also some discrete operators. We have Sm and Sn that are the forward shifts in space and time. They act like this on a function defined on the grid, so basically evaluate at the next point in space or in time, respectively. And then combining them with the identity operator, you can define the forward differences in space and time, which are the usual ones that everyone has seen. And then in the next slides, you will see also some other operators, mu m and mu n, and these are the forward average operators. So you're taking the average between your function and the function evaluated at the next point in space for mu m and in time for mu n. So this is our notation for the discrete setting. And when you are discretizing a PDE using some finite difference approximation, what you're doing is just replacing the derivatives with some difference. So instead of having a partial differential equation, you will have a partial difference equation, which is not in this way, that depends on the points in the lattice and on the approximation of u at the grid points. And again, you can define conservation laws in a very similar way. Formally, it's the same expression that the continuous case, but instead of having total derivatives, you have here the forward difference. So forward difference of some discrete flux plus forward difference in time of some discrete density. And they have again to be 0 on solutions of your partial difference equation. So the definition is very similar. And when they are in this form, you can always write them in this form, as in the continuous case. You say that your conservation law is in characteristic form, and this function here is called the characteristic. So everything is really parallel to what you've seen in the continuous setting. And the very fundamental result for us is due to Cooper-Schmidt. And you can define a difference Euler operator. If you remember how the continuous Euler operator is defined, this is very similar. You just have shifts here and the adjoint of the shift operators and then the total derivatives. And the kernel of this Euler operator is the space of the difference divergence. So it's really the analogous theorem for the discrete case. So if you can find a multiplier Q tilde, such that the product A tilde times Q tilde is in the kernel of this Euler operator, you have that this product is a divergence and therefore a conservation law, because it will vanish on solution of the partial difference equation. So our strategy is somehow revealed already, because our goal will be so you have your PDA, you want to find an approximation I tilde, you have your conservation law that you want to preserve, this has a characteristic, you want to find an approximation Q tilde in such a way that, well, they need to be accurate enough, and that product has to be in the kernel of the Euler operator. So this is guaranteeing, this will give you the guarantee that you are preserving a discrete version of the continuous conservation law, because Q tilde will be an approximation of Q, A tilde an approximation of A, and the product is there, so it can be written as a divergence. So in order to better understand how we are going to impose this condition, I'm going to consider basically as a benchmark example given by the BBM equation you've seen before. And it is just a very simple PDE with a third order linear term. It's very simple to the most famous, maybe, the reasonable differences on the highest order derivative. But different than KdV, there are no versions in any conservation law, but there are only three that have a physical meaning. The first one is the local conservation law of the mass, then the local conservation law of the momentum, and then the one of the energy. And all of these three can be written in characteristic form, and the three characteristics are these three. You can see that the first one is just one. This means that basically the first conservation law is the equation itself. It's just written in conservation form. The other two instead depends on u and the derivatives. So I'm going now to introduce what is the strategy that we are using to find this method step by step. The first step is very easy. So first of all, you have to choose the accuracy that you want for your scheme. So we are going to limit this conversation to this talk only to second order accuracy, and then check what is the stencil, the minimal stencil at least that you need to have such approximation. So you need to check how it's A, how we are Q. We can see that the highest order derivative is this one, and this means that you need at least a stencil with 6 points. So this is the minimal stencil. You cannot take a smaller one, but you can take a bigger one if you like. That's really the minimum example for having second order accuracy. At this point, once you have fixed the stencil, the second step is to consider the most general finite difference approximation of every term in A tilde and in the conservation, in the characteristic of the first conservation law that has second order accuracy. Now, in our case, we have that A tilde is only these three terms. We have a stencil that has only 6 points, so that immediately determines what will be our approximation of the highest order term. So that's already determined. Instead, for the other two terms, we have some freedom. So we have some coefficients here, alpha, beta, and gamma. They have to satisfy some relations because we want second order of accuracy, but you still have some freedom there. Not all the terms are fixed. And then we have to consider the characteristic of the first conservation law. For us, it's just one, so there's not much to do there in this case. The third step, so we have some freedom here. We want to use this freedom for preserving the conservation law. So basically, we want to find the values of alpha, beta, and gamma in such a way that we are preserving, first of all, the first conservation law, and then we can see what we can do if we can do something better. And the idea is to solve this equation here. So this is the solver that will tell us what are the values of the parameters that will give the conservation law, first of all, the first conservation law. We need to solve this symbolically. This is quite easy in this case because Q1 is just 1, but in general, the characteristic depends on u and on the derivative. So there are more parameters that will come from the discretization of Q. Here we don't have any parameters just because it's 1, but in the other ones we will have more free parameters that we're going to multiply each other here inside. And solving symbolically this condition here is very complicated and requires in general very long computation time. And we can see, for example, to better understand this, what happens in our case where everything is polynomial in the variables u, I, j. So when you multiply Q tilde with A tilde, since they are both polynomials, you don't have any other kind of nonlinearities in the BBM equation, you will still get a polynomial. And when you apply the Euler operator, it's still a polynomial, because what you're doing is just differentiating and shifting backwards. So that's a polynomial in the UIJ. But remember that inside Q tilde and A tilde, you have some free parameters, alpha, beta, and gamma. They appear in your polynomial inside the coefficients. Now, for having the conservation law, what we want is that this polynomial is identically equal to 0. So all the coefficients of this polynomial have to be 0. So for each coefficient, you have an equation to solve. And this equation is in general non-linear for this polynomial because things are multiplying each other here. Parameters in Q are multiplying parameters in A, so they're at least quadratic. Moreover, if you have polynomials and you have monomial with degree d, a power d of u, or one of the derivatives, this is going to introduce in your system and about n power d new unknowns. So this system is very complicated, it's a very huge system, along with a lot of equations and a lot of unknowns. And you need to solve it symbolically. So that's where everything becomes very complicated. So one idea could be to use the Grosvenor basis to solve this polynomial, but this system, but this requires a very huge amount of memory and very long time computations. Imagine that for the BBM, where we have only quadratic nonlinearities, and we're using a small stencil, it takes like weeks to get a solution. So this is not making the strategy very practical.
So several dimensions means n to the d, n to the d is the...
So it's like if you have a power of u. So in our case, d is just 2, because we have quadratic nonlinearities. But if you have a cubic term, and imagine
d is the degree of the polynomial.
The degree of the polynomial, yes.
But if you have several dimensions, space dimensions, you would have also n...
For each term that is cubic, for example, we will have n power 3. It's a combinatorial formula, but yes, it's proportional to that. Not if you have like a stencil with 10 points, it will be not exactly 1000, but it will be like 300 for one term that is cubic. If you have more than one term that is cubic, you will have other 300 variables. So things become very complicated already with quite small stencil and not higher degree, not very high degree linearities, non-linearities.
Can you remind us about the Grosvenor basis? Its characteristics?
The Grosvenor basis is a technique used to solve polynomial equation. I think Liz knows much more about that than I
Laplacian
do.
elimination for
It's basically,
polynomial equation. It's similar. It's not
Okay,
like...
okay. It's a double exponential algorithm. That's what you need to know.
Okay.
That's exactly what I need to know.
Yes, actually, in fact, I never used Grosvenor basis to use this. I just needed to know how long it takes not to use it for this kind of problem.
Don't tell Evelyn Hubert.
Well, so the idea is to make this strategy a little bit more practical by reducing the number of parameters of unknowns that you have in your system. And one convenient way for doing that is to identify some key terms that usually are the highest degree nonlinear terms in the characteristic and make them as compact as possible. So without using the whole stencil maybe, but only the minimal amount of points that you really need for your accuracy. In that way, your system magically can be solved in a few minutes rather than in weeks, because things will become very simple. Some of those equations become linear. You can solve them one by one, and so by elimination, basically, you can solve the whole system in very short times. So once you've done an ansatz, that should help you solving the symbolic computations, you try to solve this condition that will give you the first conservation law if you're able to solve it. If you're able to solve it, you will have the guarantee that this can be written as dm of f tilde 1 plus dm g tilde 1, where these are approximations of the continuous flux and the continuous density. After this, in general, you have still more freedom. Some of those parameters are not totally determined. You still have some freedom in the alpha, beta, and gamma that I introduced before. And you can try to iterate the procedure with a new characteristic. So you choose another conservation law and iterate everything from the beginning with a new characteristic. So this is basically the strategy that we are using. For the BBM equation, we have been able to solve these two conditions that give the conservation of the mass and of the momentum. And our ansatz was just choosing the Q tilde 2 to be as compact as possible. Q tilde 2 is just U for us. Choosing it in this way, you will be able to solve everything very easily, and you will be able to fix all the free parameters in your discretization except of one, lambda, which is left, and this will give you a family of schemes. Of course, you can write them in conservative form because we are presenting the mass. And everything here is a second order approximation of the continuous counterpart. The only difference with the continuous case is that you have a factor here, lambda dm, that doesn't appear in the continuous case. But anyway, that's not a problem, because this parameter, that is the free parameter we have, is always a big O, delta x squared, delta t squared. So as soon as your step size are going to 0, this term that doesn't appear in the continuous counterpart is going to vanish. And anyway, it's a perturbation that you're introducing. It is second order of magnitude with the step size, so it's consistent with the accuracy that you are requiring for your method. And this is the conservation law of the momentum that we preserve. You can see that I give you only the approximation of G2. You can see that it is a second order approximation of u squared plus ux squared, that is the continuous version. And then you have this term here that doesn't appear in the continuous density, but is multiplied by lambda, so no problem with that. If the expression of the flux is a little bit too long, so also to write in a slide, and so you can find it on archive if you're interested. But what I'm going to say is just that it's also that a second order approximation, there will be lambda appearing there. So similar to what you've seen for G2. At this point, we have still a free parameter here. So of course, a natural question is, can we iterate the procedure again, find an approximation of the characteristic of the energy, and fix lambda and this approximation a way to preserve also the energy? This is something that we have tried, but we didn't manage to find any, well, there is no value of lambda and of q tilde 3 in a way to preserve also the energy. In that case, so what you can do is try to extend maybe your stencil, so giving more freedom and see what happens. Or maybe you need to change the ansatz, the simplifying ansatz that we did at the beginning to simplify the calculations. We have done some attempts, so on the same stencil, we have found one scheme that preserves mass and energy, but not the momentum. This is the family that I just introduced, and then we have tried with wider schemes, and this is what we have obtained. So one scheme only that preserves the mass and the energy, and then another family that is wider. It depends on two parameters. They are both, anyway, perturbation of the second order that preserve mass and momentum. And if you want a family of energy conserving scheme, you can go on a 10 points stencil. And this scheme is particular. In this family, there is a scheme that is already known in literature, which is the one that you obtain with lambda equals 0, is this one. And this has been obtained also using some discrete gradient method. So for example, there's discrete variation derivative method, and it can be obtained also by using the average vector field method. So it can be obtained also using discrete gradient methods. And this is not something that actually surprises us, because in this reference of McLachlan and Quispel, they prove that discrete gradient methods, when they are applied on a suitable discretization in time, they are able to preserve locally the conservation law. So it's not so surprising that we are getting some discrete gradient methods when we apply this strategy to Hamiltonian PDEs like the PDM. And I'm going to show you a numerical test, also to see how the schemes work compared with other schemes in literature. The numerical test that I've chosen to show you is the interaction of two waves over the interval -1 to 100, and we are integrating till time 15. We are using periodic boundary conditions, but not because we need them, just because it would be easier to evaluate the error in the conservation laws if you're going to consider the error instead of the global invariance. But we know that you're presenting the conservation law exactly, and for other equations, we've actually done experiments with the Reclay conservation laws, for example, that are not conservative. So this is something just that helps evaluating the errors, but not required. And this is the grid that we are using, and we're going to compare with some multisymplectic schemes. One has been introduced in this reference for the BBM equation, and the other one is the most famous Pressman box scheme. And we're going to make the comparison in terms of error in the solution and error in the global invariance. This is why we have set periodic boundary conditions, so we can easily check the error on the conservation laws as the maximum error in the global invariant at each step. And this is the result. So maybe you cannot really see the difference in the colors, but okay, the gray ones are the energy conserving schemes, and the blue ones are the momentum conserving schemes. You can see that the mass is exactly preserved by all the schemes that we've considered. Also these two, because they are actually in conservative form. Momentum is preserving that by the momentum schemes as we expected, but not by the energy conserving. There is still some small error here. The energy is exactly preserved only by the energy conserving, but not all the other schemes. And for the families, where we have a choice on the parameter, I'm giving you two different values. One is just 0, so without introducing any perturbation in our equation, and the other one is instead the value that gives the best error in the solution. So let's say it's the optimal value of the parameter to minimize the solution error. And you can see that the schemes are about comparable. The accuracy of the scheme is quite comparable with the one of the multisymplectic schemes, but becomes much smaller when you're choosing your parameter in the optimal way for these three families. And this is basically the solution that the problem that we are studying. The dashed solution is the initial condition. So what is happening is that the waves are moving leftwards from right to left. The fastest one is overtaking the slowest one as sub point. But for the BBM equation, this interaction is not of solitonic type. So the two waves at the end are not unscattered, and there is a small oscillation tail here, which is it's not a numerical artifact. It's something that has to be there, and it's generated after the interaction of the two waves. And in order to make the comparison, because all the schemes are very accurate, so if I'm going to show you everything on this scale, you will not see any difference because all the schemes are very accurate. We need to magnify on some zones. That will be these three. So this is what happens on the top of the faster wave. We have the continuous solution, which is the black line, and then the solution of the multisymplectic are the ones, the red and the blue ones. And the purple line is the solution obtained by the discrete gradient method in our family, the EC10 0. Instead, the circles that are basically overlapping the continuous solution is what you get if you choose the parameter in the optimal way. So you will be able to find, there are schemes in our families that are very accurate. The problem at the moment that is still part of the research is how to find exactly this parameter without comparing the solution error. Because if you don't have the solution, you don't know how to choose the parameter. So we know that there are various of the parameters that are very convenient, but we don't have at the moment a criteria to determine them a priori before doing the calculations.
Sorry, could you go back to the table? How did you compute the errors there? I missed that.
The errors, so
for the conservation.
The preserved ones,
Yes.
for the preserved ones where we have this model, we are able to find, so once you have the conservation laws, yes, you solve this, and then you can find the flux and the density.
But those will depend on the stencil you're using.
Yes, yes.
So for each,
but for the ones that we have the preservation, we are able to determine what is exactly the invariants that we are preserving. So once you have F and G, with some we have periodic boundary conditions. So this part will vanish, and what we are preserving, we know it is the sum of the density. So that is evaluating the error on the density at each step, the maximum that you get at each step. Instead, for the ones that they're not preserved, we are just using the most simpler approximation that you can think. So, for example, central difference for a first derivative, or just u for u. So, when it is preserved, we know the formula. Otherwise, we just use the simplest one. And in the for the slower wave, this is what happens. Again, the multisymplectic schemes are the red and blue, and the two conservative schemes are actually equivalent here. They're very similar. They're doing a very good. They're providing a very good approximation. And this is instead what happens where there is the oscillatory tail. All the schemes are very accurate also here. The highest order, the highest error is like 0.02, but the one that best approximates the tail is the press one box scheme in this case. So this is part of the solution. So the schemes, let's say, they work more or less conveniently depending only on the part of the solution you're looking, but here all the schemes are doing very well. The maximum error is very small. This theory can be extended also for a system of partial differential equations, but things become a little bit more complicated, because if things were already complicated for the symbolic calculations, when you have one single PDE, things will get more complicated if you have two PDEs instead to preserve, and in particular if you have a cubic term and then a quadratic term. So this is just a more complicated example, but the theory can be extended as before. And this is the equation for the complex variable, but you can isolate the real part and the imaginary part, and you will have a system of two equations that you can write in this way. So a system of two PDEs with cubic nonlinearity. The nonlinear Schrödinger equation has infinitely many conservation laws, but these three are the ones that have a physical meaning. The first one is the conservation law of the charge, then the momentum, and then the energy. And these three conservation laws can be written in characteristic form, and these are the three characteristics. So you can see that now everything depends on the solution. We don't have anything that is constant as before.
Sorry, U and B are, U is the real part of psi,
Yes, yes,
and B
yes.
is the imaginary part of.
Yeah, exactly. So I didn't say that, but yes, yes. And now just, of course, you can use the compactness assumption that I've showed before, but just to show something different. Different ansatz that you can do is to start with an already known semi-discretization. So in our case, for example, we have this semi-discrete model that is the Ablovic-Slavic model. It's a semi-discretization of the nonlinear Schrödinger equation that is integrable, and but is continuous in time. So our goal now is to use our strategy to find time integrators for the Ablovic-Slavic scheme that preserve conservation laws. And so we are doing exactly what we were doing before. On the stencil here is again 6 points, so it's the same that we have used before. We want again second order accuracy. And we solve these two conditions where Q1 and Q2 now are completely undetermined. So now our ansatz is just on the semi-discretization. Here is the most general second order approximation of the characteristic that you can have in your stencil. And solving these two equations, you will be able to find three different schemes. One is this one, that I denote with MC, momentum conserving Ablovic-Slavic. And it amounts basically to apply the midpoint method in time to the Ablovic-Slavic scheme. It preserves second order accurate approximation of both the charge and the momentum, but does not preserve the energy conservation law. So whatever you choose for Q3 you will never be able to preserve the conservation law of the energy with this method. The other two schemes can be written in compact way both together in this form, whereas here is not a free parameter as before lambda. It can be just 0 or 1, so you have only two schemes here. And the difference, also with the one we've seen before, is only the way this linear factor is approximated. So in this, before we were just approximating it on the central line. Here we are taking two couple of nodes that are at the corner of your stencil, so or along the first diagonal or along the other diagonal, and each of them is a method. The good news for this two scheme, there is a good news and a bad news. The good news is that you can find an approximation of the characteristic of the energy in such a way that you can preserve in such a way that this condition is solved. So you are actually having three conservation laws. The bad news is when you look at the truncation error, because the conservation law of the charge is actually an approximation of the continuous conservation law of the charge. But if you look at the momentum and the energy, there are some ratio of the step size, which would be still fine, because here, for example, you can choose delta t small enough with respect to delta x and have a second order approximation of the momentum, but then you realize that this quantity is one the inverse of the other one. So if one is vanishing, the other one is becoming bigger. So you have three conservation laws here, but at most two actually are approximating the continuous ones, depending on how you choose the step sizes. So you can use again compactness assumptions to simplify the symbolic calculations, as we have seen for the BBM, and we have found family of schemes in this case, but neither of them preserves three conservation laws. One family depends on one parameter preserves charge and momentum, and one that depends on three parameters that preserves the charge and the energy. And again, if you set everything equal to 0 here, you will find something that has been obtained already in literature using the discrete variational derivative method by Furiata and collaborators. So I'm going now to show you some numerical tests comparing with known schemes. The first one is a multisymplectic scheme again. The other two instead are invariant conserving methods. So they are coming from a method lines approach where you are first discretizing in space and then applying a method for ODEs in time. In the first case, we are using a symplectic scheme in time that will preserve quadratic invariants. In the other case, we're going to use an energy conserving method in time that will preserve instead the energy. And the first problem is just a single soliton that is working over -2020 till time t equal 2. And we are choosing the grid in this way, where delta t is smaller than delta x in this first example. And again, we are going to compare the solution error and the error in the conservation laws. There is nothing really surprising here, so conservation law of the charge is preserved by all of the schemes. These two schemes here are preserving the three invariants, but we have delta t is more than delta x, so we don't expect the energy to be a good approximation of the continuous one. And here, the energy conserving schemes are actually preserving the energy.
What is that?
Yes, I'm going to explain that, because now you see that there are three different values of the three parameters where we have a choice. The first one is again 0. The second one is again the choice that minimizes the solution error. The third choice is the one that minimizes instead the invariant that we are not preserving. So for example, the energy conserving, we are trying to minimize the error in the momentum. And for the momentum conserving, we are trying to minimize the error in the energy. This is a criterion that can be used. In this case, gives good result, but doesn't always work for all the momentum tests. So sometimes the error in the non-preserved invariant is preserved, for example, by a very high number, so like 100 or 200. But remember, this number cannot be too big, otherwise the perturbation is not anymore a perturbation. It will be something that is going to destroy the convergence of your method. So as soon as you see that this is going to happen for 1000, for example, you can already reject that solution. So this is a criterion that works in this particular case of the soliton, but doesn't always work. Anyway, here all the schemes are basically comparable to the known scheme. And again, if you are able to spot what is the best value, you will have very nice convergence properties, very nice accuracy. And this is what happens at the top of the soliton. So again, I'm magnifying because all the schemes are accurate. And these are the different schemes. The multisymplectic. This is the symplectic scheme, but if you consider the energy conserving scheme or the discrete gradient in our family, it will overlap this line more or less. And the black line is the exact solution, and the blue line is the most accurate of our schemes. And to conclude, I'm just going to show you a last numerical example, which is a breather kind of soliton. You start with a cosine, and you will get this kind of oscillations and a kind of a periodicity also in time. So it will be very important to reproduce very well the frequency of these oscillations. And we are setting now delta t bigger than delta x, opposite as before. So we expect here that these schemes are actually preserving better the energy, and the approximation of the momentum that we are preserving is not actually converging to the continuous one. And so here, for example, I'm giving you again only two values of the parameter because that criterion doesn't work over minimizing the non-preserving scheme. It will give you a very high number of the free parameters, so it's not a good criterion. Maybe you can try to give some kind of tolerance on the amplitude of the parameter. And you can see here that all the schemes are preserving the momentum, but this is just a numerical artifact. It's due to the symmetry of the solution, the symmetric shape of the solution, and the way how we are approximating in the most natural way the momentum. So it's just a numerical artifact. This one is not something that happens in general, that the energy conserving preserves also the momentum and these kind of things. And again, all the schemes are compared quite well, very well, with some better, some worse, but they are all comparable with the accuracy of the known schemes. And this is what happens when you plot the modulus of the solution at the final time. So the black line is the continuous, the exact solution. Well, it's a reference solution because we evaluated with a higher order method and with a finer grid, so we can trust that that's the real solution. The blue line is the most accurate of our schemes, and the other two are the midpoint and the energy conserving scheme. The multisymplectic will overlap the purple line. You have an error here in the modulus, which is about 0.2. But if you check the phase, it will be even worse for the known schemes, whereas our scheme is approximating very well both the phase and the modulus. It deserves some more words. The comparison with EC0, which is the discrete gradient method in our family, because this is actually the best value of the parameter that approximates the modulus of the soliton. Here we have an error for the blue line, which is about 0.02. But if you check the phase, you will have an error for the discrete gradient, which is about 0.1. So it's bigger than the error that we were committing before on the modulus. So if you check then how good the single components, the real part, and the imaginary part of the solution are approximated, you can see that it is worth to use the optimal value of the parameter if you can find it. But if you are approximating the modulus, this is the real part, and analogous one for the imaginary part. But if you're trying to reproduce the modulus, the discrete gradient is doing is giving a better approximation. So to conclude, I will just recap what I've talked about. It is a new strategy to develop 5 different schemes that preserve conservation laws. It is based on the fact that both in the continuous case as in the discrete case, there is an Euler operator, and the conservation laws form the kernel of that Euler operator. So this is the conditions that allow us to preserve the conservation laws in the discrete. And we have used this strategy not only for the 2 equations that I've showed you today, but also, for example, for the Poisson medium equation, which is not Hamiltonian, the KdV equation, which is integrable, then KdV equation, where there is a higher degree nonlinearity. And in general, what you get are families of schemes. There is always this freedom, they depend on some free parameters. And we are still looking for a way to spot immediately what is the way of fixing this parameter in order to have the best accuracy. But there are criteria like, for example, trying to minimize other conservation laws that can be used. But we need to be careful because sometimes they don't give good results. So that's my talk. So thank you for your attention.
Some questions?
So if I come to you with a random PDE with random conservation laws, so the very hard thing in this will be probably to get the coefficients right, such that you get the discretized conservation laws. So do you know the complexity of your algorithm?
No,
because if you use Buchberger's algorithm or do the Gribner basis thing, then it would be double exponential.
Mm-hmm.
So it would be so you would, I mean, unless there's some extra structure, it must also be double exponential, because otherwise you would be better than that.
Yes, in fact, the trick, let's say, is using those compacting assumptions such a way that you can solve everything by elimination, basically. So once you're specifying some of the coefficients in A or Q, you're specifying them, that is not anymore quadratic. Some of these equations become linear. So you can solve it, find the solution of a few of these equations, replace it in the equation that are actually polynomial, and everything becomes linear. So
through this
he uses his brain and reduces the things at the beginning, right? When you do something at the level of...
Yes. At the beginning, I
I
specify something in my discretization. If you want to do it in total generality with all free coefficients, I've never used that algorithm, but it's what Liz said, basically using the Grobner basis.
Then it would be like double exponential. Okay.
Yes. The thing that should be said also that you will mention is that what I've done now is dealing with polynomials. So in that case, you can use the Grobner basis because you will have a system of polynomials. But if you have a different kind of nonlinearities, this is something that we need still to investigate.
Yeah. Okay, but you don't have an estimate of the complexity of your strategy.
No, I mean it's Gaussian elimination basically. Finally, if you
again,
but it's like a Gaussian elimination basically. It's yes, because you will reduce your equation to be a linear finally. So it's like solving a system.
The double exponential is without any human interaction, and it's worst case. What he's doing is using his brain.
Should be careful with that.
To find a good corner to start. It's going to unlock all of the rest. So it's sort of.
This is why
It's not all purpose. It's bespoke for the particular equations that he has.
It's the Taylor.
Pardon?
It's the Taylor.
I want to ask a completely different question. You are generating your methods by having this goal of preserving some conservation of local conservation. How about convergence and stability of the method? What do you know about that, and how can you trust that your generated methods will have this nice convergence and stability?
But The convergence we are analyzing by using the Taylor expansion. So we'll see what is the local truncation error, and if that, for example, for this conservation laws.
You need stability, right?
For the stability, since we are preserving the invariants, like u squared, once we know that u squared, for example, is preserved, like the momentum. For example, for BBM, we have that is preserved the u squared plus
You
ux
have
squared.
convergence proofs.
Once you preserve the square, you have global stability in time.
Yeah, but I'm not just happy with that.
No, but okay, but
We know
you have
that the
stability.
approximation of u and ux that we are preserving is a second order accuracy of the continuous one. Second
Yes,
order
but my
approximation.
method could be unstable, right?
Also, you
If it's unstable, then even if I have consistency, I might have not have stability, not have convergence, and these are nonlinear problems, so it will be difficult, I guess, to prove convergence in general.
I think he gets the stability by preserving the. I mean,
this is what I thought, my man.
when you preserve the u squared, you are preserving the norm in time, and then you are preventing the solution to blow up in finite time, which is
This is what
once you have,
But
I mean, you
can
have the stability in
but
time.
this is not true because you cannot blow up in the H1 norm or something, right?
Okay,
So-
but this is okay. Then you have to go to another
Gradient,
method.
yeah.
Yeah, I agree with you.
Yeah.
I mean, the choice of the
Yeah.
norms, it really depends. But
But can I ask
I think it gets-
really
I think it
different
gets-
question? But so now the way I see this strategy is that you have kind of a machinery for the continuous case that was partly explained by Peter, and you kind of you set this in the you put this into the discrete setting using discrete Euler operator, discrete versions of everything. But can you connect the two, for instance, by the means of the modified equation? Is it possible to construct a continuous modified equation having local conservation laws which are the same ones?
I haven't tried to see what happens to the modified equation.
Right. I think that could be quite interesting to see.
You have used periodic boundary conditions, but your test function is not periodic. Have you checked that your errors isn't perhaps dominated by age effects?
So which one is the?
The solitons, the secants.
Oh yes. We don't get.
They're
to
not
one.
periodic, right?
No, but we don't get. We stop the simulation before getting to the border. So we take
Yeah,
it.
but what do you mean? I mean, those things don't decay that rapidly.
Mhm.
They don't decay as rapidly as Gaussians, for example, right?
Yes.
So you have checked the edges and his.
Yes. That, yes, I haven't showed you the picture, but yes, it's quite smooth at the edges. So we haven't started
I mean, when you talk errors on the order of 10 to the minus 13, you know.
So nothing bad happens to the boundary because otherwise we will not get so low numbers. But again, periodic boundary conditions are just used for showing those nice numbers. So you can just change.
That I understand, but you have to be careful, right?
Yes. Thank you.
All right, it's getting a bit late. Maybe you will still be here for a long time.
Yes, till
Gianluca?
the end of the program.
Yeah. So he's sitting in room number
M5.
M5. So just feel free to come and ask questions. Let's thank